Alright, time for another draftphysics.com, debatephysics.com also. And so part 3 of this argument. And I suppose it has to be argued out because this is what, people just keep contriving excuses to keep believing, which I just don't understand. Because I asked the simple question, right? I mean, you really don't believe, right? DB guy, you really DB guy, you don't really believe it takes 25 times the fuel to spin a motor 5 times as fast. And you kind of know, right, with like a water wheels and different mechanisms, I can't just change the velocity of the water. I have to change the momentum of the water to get more power out of the water wheel. So this is a moot conversation. Again, the rocket, calculating the kinetic energy of the thrust will do you no good because the equal and opposite reaction is going to be completely controlled by the momentum. So this is such a, it should be a moot subject because it's just, there's no foundation for believing this crap. There was never any evidence from its origin. It's just a fable. All right. So, continuing. Alright. If I hit a cart with a rubber ball, the more the cart moves, the less reflection I'm going to get. That's a quote of me saying the obvious. And the actual fact is, their theory says I'm going to create more momentum going. The more momentum I push into the object, that is, the closer I get to that twice as much momentum in the object I hit with the tennis ball, the more I get back from the tennis ball. The tennis ball doesn't bounce back very far. If I put less energy into the frickin' goddamn object, I get less of a reflection. That's how their theory works, which is completely backwards. I mean, the more you put in the object, the less you're going to get back. The less you put in the object, the more you're going to get back. True, he says. So again, so what's the point of saying true? Because that's the explicit. We've been over it, okay? I mean, at a 1 to 10 ratio, you're putting 180 momentum, right? You put 100 in, and you got 180 going away, and you're going to get 80 back. You're going to get a lot back. So the more energy you put in, the more the wall takes the energy. And he keeps turning it into a velocity. It's not a velocity question. It's a momentum question. It's how much mo is in it. Oh, it's just so stupid. The less velocity when the mass is 10 times the velocity, when the mass is 10 times the mass, it's going to be 1/10 the velocity is the same amount of energy, the same amount of momentum. So, of course, the velocity goes down, but the momentum's going way up. Given to the other object, but not less momentum. So here he says it again, but not less momentum. True, the more reflection means less velocity given to the object, but not less momentum. Of course it's more momentum. 180 is more than 133, right? If it's a 2 mass object, I'm going to get 133. If it's a 10 mass object, I get 180. Clearly 180 is more. Clearly, I put more in and I got more of a bounce back. I only get 1/3 the velocity back on the 1 mass object when I'm hitting a 2 mass. I just get 1/3. So again, you're just contradicting the actual experimental facts. All right. The more the cart yields, the lighter we know it is. So that's even more ridiculous. The more it yields, and the whole yielding point is the amount of goddamn momentum or energy it's absorbing. I'm not talking about its velocity. I'm talking about how much energy it took to move the object. How much energy it took to move the object. Oh, shit. Let's try to think analytically what happens in collisions with a reflection. Well, this is the only important thing to get to is yes, because this is where all the misunderstandings exist. The interaction can be divided into 2 parts. No, it's more than 2 parts. Alright, in the first part, the reflecting object goes from its initial velocity to 0 velocity. So in hard kinetic objects, this might be true, but we know in springs that's not the truth at all. So let's go through what springs do. All right, so let's go a little further. The movement can't change in the opposite direction without the movement of zero velocity. So yes, there is always some point where they stop, but whether, well, I shouldn't even say that because it's not true. Okay. Correct. To conserve momentum, we probably agree that the initial momentum of the reflecting object must now be in the other object. So we know that all the momentum isn't transferred. That's the whole point here. Is that as soon as we go from a 1 to 1, as soon as we add 1.1, we're starting to create a little tiny bit of a reflection. It's not perfectly giving all of its energy to the other object. Now, I would argue that I think it is almost entirely going into the first object all the way up to the 1 to 2 thing. The 1 to 2 mass is when you start changing the rules, because that's when you got the 33 going back this way. You got the 1/3 the velocity coming back, and I would argue you have 1/3 of velocity going forward. But anyway, all right. So let's see. In the first part, the reflecting object goes from its initial velocity to zero velocity. The movement can't change to the opposite direction without the movement of zero velocity. All right. So let's get to the second part. In the second part, there is the reflection. What causes the reflection? Well, my simple argument is you only get a reflection when the energy isn't absorbed. So the object can't take the energy at the speed you provided it, and so it reflects it. Like you could almost argue a bullet bouncing off of something, glancing off of a surface. It doesn't absorb much energy, the surface. It doesn't take much off the bullet, okay, but it does change the direction. And again, the classic example is gravity. I throw something up into gravity, there's not twice as much force that pulls it back down. The gravity doesn't do twice the work. Okay, it just consumes the energy going up, and then it gives it back going back down the other way. So it changes the direction with no net use of energy. All right, it must be a force that the objects apply to each other. What else could it be? So again, you want to just, I mean, I've already gone over it so many times what I think the force actually is, and you have to actually possess it. It's a thing. The force is an actual substance. There's actual energy going this way and energy going that way, and you have to have a differential in that energy to move in a direction. What else could cause the movement other than some force between the objects? So again, this isn't, how is this a relevant point too? I'm the one defending the idea that it's made out of a force that's a real, that just like Newton stated, it's a quantity of motion. All right, one way to put it is that the objects push each other. They have to, that's right. What happens when two objects push each other? They gain momentum in opposite directions. So again, they only gain momentum in opposite directions if one of them is non-movable. If you push against a wall, right? I mean, they have this experiment, right, where a person pushes on some other person on a skateboard, and they push. Just one person has to do the pushing. So one person pushes. They go off it, if they're in reasonably equal masses, they go off with equal directions, right? But their velocity is going to be a lot higher if the one person pushes against the wall. The same push, the same amount of force, but all of the force will end up moving them. So I could just argue right there that experiment proves the point that, you know, there's only so much momentum generated by the action, and when you make two things move, that's twice as much work, and you're only going to go half the velocity. So do you really think that if one person pushes against a brick wall on a skateboard with a known quantity, let's say we use a spring even, right? A compressed spring, a device, that somehow if both people move, it's going to be the same, this thing's going to move with the same velocity. So it doesn't matter. Brick wall, person moves, same velocity. I'm arguing no, it's not going to be the same velocity. You're going to go a much higher velocity if you push against an immovable object. All right. You can almost use this as an argument, okay, for the fact that the thrust of a rocket engine is probably more effective when it has the ground to push against. When it has that energy being reflected back up that's hitting it again and pushing on it again. So it gained energy by throwing the thrust, and then it gains a little more energy by the thrust coming back and hitting it again. Alright, one way to put it is that the objects push each other. The other, what happens when two objects push each other? They gain momentum in opposite directions, and this is how you get to your free momentum. No, it's really not how you get to the free momentum is completely your problem, and the very idea that you think it's conceptually reasonable. So in space, I could do this. I could just have a 1 mass, then a 2 mass, then a 4 mass, then a 16 mass, and then a 4 times 16, 64 mass. I just keep going, and I can make more and more momentum. Just keep increasing the total amount of momentum. So I can put 100 in and get 1,000 out. And you're saying that's a reasonable fact of life. And all the free energy nuts are just really stupid because they haven't figured out how obvious it is you can make free energy. Alright, let's see, what else could it be? One way to put it is that the objects push each other. What happens when two objects push each other? They gain momentum in opposite directions. And this is how you get your free momentum. The objects push each other with the energy stored in the compression of the objects. So we're talking about elastic stuff, and now you're talking about some kind of compressible stuff. If you disagree, what do you think causes the reflection? The inability of you to put the energy in a manner that the surface can absorb. So if I shoot a bullet at a brick wall, the fact is, a cement wall, let's just say on wheels, the fact is most of the energy won't get into the wall because the bullet will fracture, pieces will fly off in the opposite direction, you get lots of reflections and losses of the energy, because the truth is you want the bullet to be absorbed to gain all of its energy. And it's not going to get absorbed, it's going to be reflected because the brick wall can't move as fast as the bullet. You're trying to move the atoms faster than they can move. They have static friction, so to speak. And until you convert it into 5 miles an hour, then 10 miles an hour, then 20 miles, you have to convert the energy into their motion, a motion they can accept. And they can't accept 2,000 miles an hour. You have to start lower than that. How does the reflecting object start to move in the opposite direction if it's not pushed by the other object? So it moves in the other direction because it can't be absorbed by the object you hit, and the lack of absorption means that you're going to get a reflection. There's only two choices, absorb and reflect. Alright, the theory clearly says you can't have free kinetic energy. So I don't know what theory says that. So it's not consistent with the third law. Clearly the third law says momentum does all the work and kinetic energy is useless. That's what Newton's third law says. Because every single time you hit a light object into a heavy object, you are guaranteed to create free momentum, and vice versa. If an object makes something move without losing its own kinetic energy, that's free kinetic energy. So again, I don't even understand the concept of you talking about free kinetic energy when the ballistic pendulum loses 99.96% of the kinetic energy. When you can't even combine a 5 mass and a 5 mass to create a 10 mass, and you perfectly conserve all of the momentum, and yet half the kinetic energy has somehow disappeared. And you really have no explanation for where it went. There's nothing. You can say, oh, something got deformed. Lie. Didn't happen. So it's just bullshit. If Walter Lewin really said the ball can make the earth move and keep all its kinetic energy, he is wrong. So it doesn't look. We're fiddling with this stupid infinity word. So I'll post a link to where a bunch of people are arguing. So first off, Professor Lewin, if you read the comments, 20% of the comments are arguing about this stupid thing he did, okay, in the video where he posed this paradox, so to speak, and yet didn't give you anybody an answer to it. So there's a bunch of speculations. And so he finally, in one of these speculations, links to another document where a bunch of people are posting comments about how they think it works. And clearly in all of that, there's a ton of people talking about, well, if it's an immovable object attached to the Earth and the Earth moves, blah, 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 blah. So that's clearly the argument. We don't even need this argument. Fuck the word infinite mass. All right? Because the same holds. If I make it a non-infinite mass, if I make it just very heavy, 100, so it's 100 times heavier than the tennis ball. So the wall is 100 times heavier than the tennis ball. The fact is, I'm going to put 199 momentums, okay? So instead of being 2, it's going to be 1.99. So it's almost the same. So it doesn't make any difference. And the wall is going to move with that 1.99 momentum. I mean, with that having 199% of the initial momentum going in. And the ball is going to bounce back with 99. So I went in with 100. I'm getting a reflection of 99, and I put 199 into the wall. So that's what the equation says. So let's not play with infinities and say go for the whole 2. We'll just go for the 1.99, okay? So talk your way out of the 1.99 circumstance. All right. Let's see. So if he said that, he's wrong. So again, he doesn't say anything. He just keeps asserting that this idea that there's a mass but no velocity, that somehow that means no kinetic energy, but it doesn't mean zero momentum. So even though it has no velocity, it's not zero momentum, which doesn't make any sense. And clearly the Earth argument was in there and he endorsed that. All right, I just don't believe he really said that. Well, you go read his comments and see what you can make out of them. If the ball reflects 100%, it means it didn't. So let's just say it reflects 99%. Okay, it means it didn't lose any kinetic energy, which means it didn't cause the wall or the Earth to move. See, you think kinetic energy moves something. It doesn't move anything. It doesn't move the ballistic pendulum. It doesn't move a rocket ship. It doesn't move anything ever. It doesn't do any work. It's just amazing. You have no experiment showing kinetic energy doing work. And the only way to have an immovable wall is to make it mass infinite. So again, that's just nonsense. I mean, immovable for the purposes of these experiments, no problem. Are you saying when the ball bearing is bouncing on the anvil's not immovable? I mean, what do you think's really happening? Is the Earth moving? What's happening? So the anvil isn't... I mean, I can show you the fucking experiment. Do you really have to see it over again? I mean, it's titled somewhere, 200 bounces. So if you have a nice heat-treated anvil, the steel doesn't dent, and you have a nice glass ball, it'll bounce 200 times. So what's your argument? That the frickin' anvil is moving? It's absorbing the momentum? It's clearly, there's no evidence it's absorbing it. So what's absorbing it? The only thing left is the Earth has to be absorbing it, which is, again, bullshit. And the only way to have an immovable wall is to make it mass infinite. So that's more crap. And that's not possible. So if I have the space shuttle in space and I'm outside doing work and I just happen to find a tennis ball in my pocket and I throw the tennis ball at the space shuttle and it bounces back to me with whatever, 80% of its velocity. Should I assume that I put 180% momentum into the space shuttle? That the space shuttle is now going to be moved because I threw a tennis ball at it with more energy than if I threw a steel ball at it and it stuck, of the same mass? Bullshit. All right, so let's just finish this comment, then we'll move on. If there were videos of pendulum collisions with 3-to-1 mass ratio, I'd be showing them. No, that's not what I said. I want all the ratios. I want 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 1 to 7. Why shouldn't we have that? So again, the fact that you are such weasels and you won't admit that, oh, come on, yeah, in 350 years, if physics is going to assert something, they really should be able to by this time, create really nice piece of evidence of this experiment. You know, filmed exactly the same way, just change the mass and see what the damn thing does. Have nice precision made masses and do the experiment right. And instead of saying, yeah, this really should have been done by now by physics, by scientists in lab coats, not assholes in dirty attics or basements, it's just such bullshit. But there are, and you have seen them. So you're saying that those videos are good enough quality. You measured the velocities correctly, you know it for sure, blah blah blah. I'm saying, of course not. We didn't even get good measurements of the heights. I mean, it's all just complete bullshit. All kinds of parallax in the fucking view of the thing. Just absolute crap videos put up by people, by the way, who you should at least concede they really should take down the videos that they know are flawed. So, the Spar has a milk carton video, complete live video. Okay, obviously things with this big an arc and things with this big of an arc aren't going to hit the carton in the same with the same amount of energy because their arc isn't even big enough. One of them's going to have 50% of its energy left at this point. The other one's only going to have 10% of its energy left at this point. So obviously it's a bullshit experiment. He left that video up. So these are the characters that you're defending their science. People who leave videos up where they know it's wrong. Alright, you've argued that we can't get accurate velocities from them or something like that. Well, damn right I did argue that. This is why I suggest the simulations. What would a fucking simulation do? So I'll just draw it again and just say, what the fuck do we need a simulation for? The math is so simple, the argument's so simple, why would you bother? And I frankly don't have a clear statement about exactly what's going to happen in terms of the proportions, because we haven't seen it. All right, compare them with these videos. I guess I have to do it. Well, I don't know what math you're going to use for my argument because I don't even know what I would use. It might take a few weeks. Fuck you. Because it does change. I mean, there's clearly a 1 on 2 doesn't behave the same as a 1 on 3. But what happens with a 1 on 4 or a 1 on 5? These are all open questions, asshole. You're claiming you know. I'm claiming I like to see it. But what I do know is momentum. Total net momentum is going to be conserved in the sense that you can't make free momentum in a direction. Direction doesn't matter. Energy doesn't give a fuck about direction. If I have an object moving in space and it hits a bigger object and all of a sudden now I have the same thing moving in this direction into space and it has more momentum, that's a real problem. And it's even a bigger problem if I have more momentum still going this way. Okay, that's called an expansion. So like in a closed vessel, if I did that, I'd end up with more pressure in the vessel than I put into the vessel. I'd be making free pressure. Alright, so anyway, so let's deal with the problem of springs, because that goes to another video I found that I kind of want to go get to, and so we'll argue that a little bit. So let me get rid of this. Alright, so let's just, like I said, the point is let's see, okay, well, I mean, maybe I'll try illustrating a little bit of the kinetic problem. All right, so we know if they have the same mass, right? This comes in, this one leaves, this one stops dead. Okay, so that's not complicated. But as soon as we start changing this mass, then it starts to get complicated. And I'd argue, so let's just take this arrow and say this was its velocity vector, that length. All right, if I add this to like 1.2, okay, so it's a little bit bigger now. So I put in the same energy this way, the same 100. All right, and what's going to happen now is I'm going to say this one's pretty much going to stop again because it's not enough of a difference. And the only thing that will change is this velocity vector will be a little bit shorter. All right, it won't be, it'll be 0.2 shorter in its velocity because it's a heavier mass. And when I get all the way up to 1 to 2, okay, then we get this idea that, well, you say it's 2/3 going forward, okay, so I have created 133 momentums, percent of the momentum, and I have 33 going back the other way. Now, I'd argue the only way to rationalize this is to say that no, what you got is you got 33 going this way, all right, so you only got 33% of the velocity, okay, here, times 2, which is 66, and then you have 33 going this way of the velocity, okay, times 1, which is, so 33 plus 66, you got your 100 back. And that's what continues to happen with the rest of the objects, is that you end up with that this ratio of motion where they separate at the same speed. Okay, so we know the 1 to 3 does that. So the question is whether the 1 to 2 does it. All right, so we know the 1 to 3, where your theory says it's 150 this way. You know, my theory says it's 75. All right, and that you have 25. You know, 73 times 25. Let me just do it that way. 25% of the velocity and 25% of the initial velocity. And so it's 25 times 3, which is 75% of the momentum is going this way, and 25% is going this way. And that the rest of them will do that. But that's just a guess. All right, so let's just do the spring thing real quick, because it's sort of important to understand that springs compress. So in a video I found where a guy's doing an experiment with a basketball, you know, it's just, I think it's just a huge misunderstanding. All right, so you have a big object, you have a spring, and then you're going to hit it with this other object. All right, so this one's coming in. And what's going to happen is they're not just two steps to this process. So what's going to happen is, okay, we can draw the next step. Will be that the spring will be, contact will be made, and there'll be some compression. So where's the energy? Is it in this object? Is it in the spring? Now the argument is that as soon as this object hits the spring, it starts increasing the pressure in the spring. And the increase in pressure in the spring goes both ways. So as the pressure in the spring is starting to increase, it's pushing, it's resisting, you could argue, in both directions. Now obviously this has a higher p-value, so it goes from high pressure to the lower pressure. So this one still continues to compress, but this one is at 0 pressure, okay? So it's resisting not at all, any more than the fact that it's matter that has to be pushed, okay? But so say if it was in space, you know, there's no static friction. So you would agree that if it was in space, as soon as there's pressure in the spring and the spring starts pushing this way, that this is going to move. So before this object stops and before it's completed compressing the spring, the object will have moved, okay, in this direction, and the spring is still not completely compressed. So now the pressure here, let's say, is equal to the pressure in the spring. So now the spring is not going to get compressed anymore, all right? But this one's got a head start, so it has some percentage, okay, X% of the momentum is already in it. It's already moving with some percentage of what the spring would have compressed if this didn't move. So if it didn't move, then the spring would still need to be compressed more. It would still have compressibility. And so the spring got compressed less than it would have been because the object started moving. And now the spring, because now there's 0 pressure on both sides, in the sense that both sides don't have more pressure, both sides have less pressure than the pressure in the spring, and the spring compresses, pushes back in both directions, increasing this velocity and giving this a velocity. So in a sense, this one got a head start. So half, let's say a quarter of the energy goes into it before the spring stops. So the whole spring, see, the spring moves its center of mass with the object. So the spring's motion has changed where the spring's center of mass is, changed the system's center of mass, and now when the spring expands, it's going to have less of its total it would have had if this didn't move, and it's going to share that 50-50. But this already gained X, so this one's going to have 50% of what's left in the spring plus the X it gained. And this will have 50% of what was left in the spring, you know, but that only might be 30% of the original energy. So this could get 30%, and this side will get 60%, 66, and 33. All right, because of the spring. So springs aren't the same as metal against metal, because I'd argue that the metal against metal argument just becomes one of the fact that you have a really quick contact. All right, everything has to happen fast, and so the differential in the mass, as soon as this mass gets very heavy, okay, 10 times the mass of this object, that you're going to end up with mostly just a reflection, and a tiny percentage of energy will get into the actual object. But in space, I'm not sure. And I'm not sure even in a Newton's cradle. But I am sure that springs aren't as simple as, yeah, the spring compresses and then it gives the energy. No, it compresses, creates pressure, pushes the object, then decompresses from a different location. So the object starts moving before the spring starts expanding. And I think that's a huge key point. And I'll, in the next video, play a video illustrating, you know, where you have to account for that kind of stuff. It's like having two springs in a system almost. You can almost think of it that way. If I have a spring on top of a spring, then any pressure I put on this spring, I'm going to get a lot less on this one. So if I just let the object hit, this one compresses, let's say, that much, you know. But if I put another spring above it, then this one only compresses this much. So the real force is going to be less on this bottom. Say this was a scale measuring. The scale isn't going to read the full amount of the impact, because this one's not going to be depressed as much as it would have been if it just got hit by the object. The spring is going to absorb the energy and essentially cut this pressure in half. Cut how much this spring measures in half. All right. Yeah, I'm not dissatisfied with that. Okay. So let me think over what else I need to say and such. I'm going to call it a video. Where the hell? Oh, it's the wrong mouse. So much to keep track of. Alright, just for fairness and clarity, so I asked this guy to answer 2 questions at the top of your next comment, or don't bother making another comment. Right? So either answer the questions or fuck off. So, as I've pointed out so many times, so do you really believe it takes 25 times the force, or fuel, okay, fuel or force, we'll use the F for fuel or force, to spin, okay, anything, okay, any mass, 5 times the velocity of any point on the disk? And, you know, this is true for linear things too, cars, I don't care what it's for. Do you really think it takes 25 times the fuel to get 5 times the velocity? Do you, okay, second question, do you think an 8-pound bowling ball going 16 miles per hour has twice the energy, twice the capacity to knock down pins? That is, give pins motion. that if I total up the total motion of the pins, the 8-pound ball will give twice as much total motion to the pins. Do you think that'll happen, or that it'll just be momentum? The 16-pound ball going 8. So what's going to move the pins? Momentum, which is equal. The momentum is equal. The kinetic energy is unequal. Will the kinetic energy knock down more pins? Ever. And the third question is, in a rocket, when it's taking off, okay, it's going to have a thrust, and you can calculate the momentum, you get a number, the mv of the particles, and the mv squared, 1/2 mv squared. And you get a number for those two things. Which one moves the rocket? Which one does the equal and opposite reaction? The momentum or the kinetic energy? I mean, we know we can convert these newtons into joules, so it's just idiotic, 1 to 10, right? So, well, their theory says, which is also wrong. But anyway, it doesn't matter. I'm just saying these numbers, which one will the rocket obey? Will it be given the amount of, will I be able to convert the motion of the rocket into an equal amount of kinetic energy as the thrust, or will the thrust be a lot higher than the motion, the joules of energy in the motion of the rocket? And will the momentum be equal? That is, the momentum of the thrust will equal the momentum of the rocket. That Newton's third law will be obeyed, and the momentum, okay, will be conserved, and the kinetic energy won't be. I'll have a lot more kinetic energy going one way, just like the bullet in the gun. The bullet has 2,000 joules, the gun recoil is 2 joules. No equality whatsoever. But the momentums are exactly the same. So answer those 3 points. Just so I can know what kind of lunatic you are. Okay. Because you have no evidence of any contrary fact. You have no evidence the 8-pound ball going twice as fast knocks down any more pins at all. Not a single extra pin motion. Nor do you have any evidence that the rocket gives a shit about what the kinetic energy of the thrust is. It always cares about the momentum. And I think you already do know that no, 5 times the force, 5 times the velocity. Alright. So, fuck you and such. Till the next time. So just to be clear on the point, we don't need the word infinite. So when Professor Lewin threw the word infinite wall, we don't need the word infinite. All we have to say is really heavy. So if we say 100 times heavier, then we're already up to 198. Okay, so 198%. So that's close enough to 200% that we don't have to, right? Let's not argue about it. And the results are exactly the same. I'm going to get 98 going this way, 98% of the initial velocity going this way, and I'm going to have 198% of the momentum going this way. So I almost have all of my velocity still going this way, and I have I have returned my momentum, just like throwing something up in gravity. Somehow I magically gotten all of my momentum back, and I made 200 going the other way. So I have a total of 300 momentums moving in the universe, and I started with just 100 momentums in the universe. I'm saying that can't happen. And you have to show me some evidence that it happens. And you can't do that, frankly. Alright. That's it. Probably enough. We'll say it's enough.